This was where we left off the last time.
So, like, shall we clarify a small recap things? Like, I have few
Yeah.
small things to be asked before the start of the lecture.
Yes,
So,
definitely.
yeah, I'll start with the basic one itself. Like,
Yeah.
we are saying like f of r given s1 is the probability measure function of getting the receive
No,
signal
not
r
this is
in
not the
the
probability measure function. This is the probability density function.
okay, it's a PDF. Okay,
Yeah,
PDF
it's a
of
PDF.
like getting r in the like if the signal sm like receiving r and declaring it as sm.
Yes. No. This is given that SM is transmitted, this F SM is given SM is transmitted. This is the next.
And we were saying this p into f of r given sm, right? So p represents the probability of receiving sm, no, probability of sm occurring, like while sending.
Or rather, it's not a natural phenomenon. Someone is transmitting these. Transmitter. Fine.
Yes, and this thing like p of e given m is actually probability of error occurring given that it is the m sm is sent.
Yes. Right. So now yes, so I will write this again. Suppose A is a region on this is a set of points, this is a set of points, and this is A union B, right? Then you have to integrate now if I want to calculate this, I can write this as right. Agreed?
So, so in
Yeah.
between like integration of f of r given sm, what it will give like on a so for a given region if we integrate f of
So
r given.
uh, so integral, you have done the course on electromagnetics, right?
Yes, sir.
So when we have a line, so suppose this is a real line, then integral basically equals you divide the real line into small or you divide the real line into small intervals or infinitesimally small intervals, take the value of fr and multiply that at each point and add those up. That's how you define an integral.
Yes, sir.
So if you instead of line, you have a surface, you know surface integrals and volume integrals, right? So
Yeah.
now if you have a function of two variables, fr, so r is, or rather r is fine. This is a two-dimensional, and let this f be a map from the two-dimensional space to the one-dimensional space or one-dimensional real line. Fine.
Okay, sir.
So then if I have this surface, say A, then if I want that, okay, I want f of r over A. I want this surface integral dr. What I will do is I'll take this surface, divide this surface into, again, small blocks. And since this r is two-dimensional, for each x and y, or for each, so r can be, so r has two components. For each of those two components, I will calculate, say this is, yeah, for each of these components, suppose this is, the battery died. For each of these components, let us say this, yes, this is fr1, fr2, and so on. So what I will do is I will take, for integrating here, what this is summation r1 to rn. So we divide this into n small areas and take the value of f at each area, for each area, and multiply it with the area and sum it all over. This is how I do it in two dimensions.
Yes, sir.
So you can extend this to n dimensions. Divide the space into n-dimensional volume, n-dimensional sub-volumes, and take the value of the integral over that hypercube, or take the value of the function over that hypercube and sum it over. That is how you will define n-dimensional integration.
Yeah, sir.
So now this makes sense.
Yes, sir. I got the integration, but I was asking, like, does it will give the CDF, right? Like, I'm asking,
No,
like,
it
what
won't
it
give the
gives.
CDF, it will give the probability.
Like, integrating PDF, we will be getting CDF, right? You should, like, I thought.
Go back and uh, read the previous semester's notes.
Okay, sir. Fine. Yeah. Fine, sir.
Fine. And so anyway, coming back to what we had. So this A union B, this is true.
Yes, sir.
So now we know that F R given Sm greater than equal to 0. This is from the probability from the properties of the PDF that for all R, right, 1, and therefore right. Fine.
Okay, sir.
So I can write right. I can do this.
Yes, sir.
So based on this, what I can do is that now since D or DM complement equals union of I have this. This is where we started.
Yes, sir.
See. So therefore integral, and I want to calculate this. Right. This is the probability of error.
Yes, sir.
Yes, sir.
Yes, this is the probability of error that you basically send SM and it lands up in some other region, or it lands up in the decision region of some other variable, and which is DM complement. So this I can write as union M dash not equal to M T M M complement right,
Yes, sir.
which is less than or equal to summation integral right?
Yes, sir.
Or right?
Yes.
Fine. And this is since so we have a bound on an upper bound. Or the worst case performance of PEM by replacing the union operation with a summation. Fine. And because of this, because we are playing around with the union bound, so because we are playing around with the union and the summation, we call this is called the union bound. Fine. And PE less than equal to summation m equal to 1 to capital M SM right?
Sir.
So this is the
Yeah.
total probability of error in
Yes, the overall
transmission.
probability of error. But it gets better. We know that for an AWGN channel, this we had derived.
Yes, sir.
Yes, sir.
Yeah, fine. Since we had derived this, we can fine.
Yes, sir.
And so that's why we are so interested in the distance between two constellation points. Yeah, one more thing. So I would like to first finish the discussion on constellations, etc., before going for the next quiz. So constellation and digital modulation, the next quiz will be on the Saturday after we finish constellations and digital modulation. Fine.
Okay, sir.
So if that is done this week, then the next quiz is this Saturday. But if that discussion spills over into the next week, then the next quiz is on next Saturday. Fine.
Fine, sir.
Yeah, because this discussion of the union or derivation of the union bound took much longer than I expected. Fine. So for equiprobable symbols, so m times 1 over m, this is simply summation 1 over m goes to m equal to 1 to capital M. Fine. This beast. Now the question is, can we simplify this further? The answer is yes, we can. So how? We know that the Q function.
Excuse me, sir.
Yes, Kirti.
Sir, equiprobable means PR of S probability of S of M is 1 by M, right?
Oh yeah, sorry. This doesn't appear. Yeah. Fine. So yeah. Yes, now we know that the Q function is a strictly decreasing function of the right.
Yes, sir.
And for any constellation S and for any 2 points SM and SM dash within this constellation DMM dash. We had found out the minimum distance between 2 points of a constellation, if you remember.
Yes, sir. Yeah.
So since we had found out the minimum distance between 2 points of a constellation, we know that this is there. So Q of DMM dash by root 2 n naught fine.
Fine, sir.
This makes sense. Or
Yeah.
the probability of error can be further upper bounded as 1 by m equal to 1 to capital M dash equal not equal to m, q d min by fine.
Yes, sir.
So actually this should be an equal to here because this is less than equal to this. So the next equality, it should, this is equal to, so this is d min and 1 over m. So m minus 1 times m divided by m q of d min by. Fine.
Yes,
Or
sir.
the probability of error is less than or equal to m minus 1 q of d min by. Fine.
Oh, yes, sir.
So is the probability of error expression simple enough now?
Yes, sir.
Yeah. So, but if we want to push the envelope further, we can simplify it even more. We know that though this is so this is kind of tight. This is slightly tight bound, but we also know that I would insert the word also here. Also know that q of x is less than or equal to minus x squared by 2. You can try this out yourself. Therefore, probability of error this. Fine.
Yes,
Sir,
sir.
so while designing the communication scheme, or while considering the symbols and the distance between them, we try to
Yeah.
minimize the bound itself to decrease the probability of error. Or
Or rather, we want to maximize the distance between two symbols. That would so, or I would say that a chain is only as strong as its weakest link,
okay, sir.
right? So a communication system is only as good as its worst probability of error. In other words,
Sir.
yeah,
So also like we were seeing like while decoding the signal BPSK and all, like
yeah.
if you're having considered two signals, the regions were not intersecting at all, right? Like if you're having 4 or 8 signal shots, like eight different points on the constellation, each will have
Then
its own region, right?
yes, each will have its own region. That's true. But when we take pairs, those regions intersect.
Okay.
Okay, when you have this D complement, that will not intersect with anything because that is by design. You don't have fuzzy boundaries over there. That is by design that those regions won't intersect, or the decision region for two signals should not intersect. It has well-defined boundaries. If you remember, we also derived the equations for those boundaries or the planes that define those boundaries, right?
Yeah.
Yeah.
Okay.
So
Here.
those shouldn't intersect, but this uh, but the complements of those regions will intersect because there is only limited space, and a region complement means that everything except that. So the complements of those regions will intersect, and those will give us these nice bounds. Fine.
Yes, sir, fine. Got it.
Great. So this was an upper bound on the probability of error. We can similarly have a lower bound. Oh, sorry. It's of little use, so we won't visit this again and again, but for completeness, you can say that similarly have a lower bound the probability of error, or the best case scenario. With equiprobable symbols. So this is greater than or equal to dmm dash. Or if you consider the nearest neighbor, m dash is the nearest complement. Yeah, this is complement. Q of dm comma min. So the minimum distance for the mth element fine. So this basically reduces to, or rather what it reduces to is that so this 1 over m greater than equal to, actually you can say that q of d min, actually dm comma min. Yeah, so this only then will this remain the upper bound, because all the constellation points may not have a nearest neighbor. So this reduces to this, and this is a loose lower bound on the probability of is here error. Fine. So this result is just for completeness. It is used very rarely, or rather, in my 10 years of working with communication systems, I've never seen anyone use this result. But yeah, still it exists, so we have to have it. Fine. So now for something, no, let's not do this. Let's there is this one topic that I want to finish. So we haven't talked about the matched filter, right?
No, sir.
Yeah, so the thing about the matched filter is it is important, but it doesn't fit into the flow of this story. We have to talk about the match filter for. So what I'm doing now is I'm going slightly off topic, talk about the match filter, and no, let's not do that. Let's talk about the match filter towards the end. Yes. let's talk about the match filter when we finish this discussion on error rates. So now, considering the special, or considering constellations one by one. Considering so the first thing that we have is, the first constellation that we talk about is MPAM. This is 5-1T. Right? So say this is minus two. Zero is not a point. Agreed?
So we were having something like 2m plus 1 like that, right? What is
2m
that
plus
then?
1.
Minus
Just a
2m
second.
plus 1 to 2m plus 1.
Minus 2m plus 1. Wait a second. So for 3 points, so see, for 4 points, it will be minus 3, minus 1, 3, 1, 3. So 4 points, this is, so for 8 points, it will be minus 7, 5, minus 3, minus 1. So m points. So this is m minus 1 to m plus 1. So that is, oh,
So
that one was this. Actually, I'll go back to that expression precisely rather than speculating about it. And these points are between m minus 1 and 1. So the mth point, the small mth point, its expression is given by, just a second. So yeah, yes. So the small mth point is 2 small m minus 1 minus capital M. This. Fine. Now you put m and 1 over there, you'll get these points.
yeah, got confused. Okay, sir.
Okay. You confused me for a minute. Yes, anyway, so the mth point is this. So because of that, what we have is that now d min we can write as 2, and based on the average energy, this equals root over right. This is what we had calculated. I'll just cross check, but yeah, sorry, 6. This should be 6. So 6 E average right? It was, yes, the square root was outside, so it was inside the square root. So yeah, so this is d min from what we calculated, right? So now, since this is easy, or since this constellation is an easy one, we will calculate both the exact probability of error and the union bound. So now, considering the ith point, so this, or rather first let's have this. So this constellation has two types of points. One, interior points. Two, boundary points. Right?
Yes, sir.
So these are boundary points. Come on. These two are boundary points, and all of these are interior points. In case of boundary points, we get an error only when, so in case of this point, you will get an error only when the, rather let me draw a simpler constellation. So points are slightly more far apart. Fine. So in case of boundary points, you get an error. So in case of this boundary point, you will have an error. This is the boundary. This is the boundary. This is the boundary. This is the boundary. So get an error only when this goes here or this goes here. Right? Otherwise, you won't have any error.
Yes,
But
sir.
in the case of interior points, you have an error when this goes here or this goes here.
Sir, why are we considering that the symbol can only be interpreted as the adjacent neighbors?
Okay, or so I'll generalize this. Adjacent neighbors are the most likely ones. But in general, you can say that when this goes here, you have an error. This
Yes,
goes,
sir.
oh, yeah. This goes here, you have an error. Similarly, this can have an error when this goes here or here. Or this crosses the boundary. Or in other words, you can have error when the interior points due to the noise cross over in either direction. But for the edge points or boundary points, only when they cross over in one direction.
Yes, sir.
Fine, great. So now, because of this, for interior points, let's call this PEI. Equals, oh, now it has turned red.
Sir, could you once again explain the Adit's doubt?
Yeah. Adit's doubt was that, see what the arrows that I was drawing were simply pointing to the next, to the very adjacent symbols. But
Okay.
what happens is that it need not, these need not be directly towards, or these need not be adjacent symbols, any symbol. So this can be misdirected as this can be misdirected as this as well, depending on the magnitude of the noise. So the way I was drawing it was not totally right.
Okay, so there's a possibility also, like here you're not drawing it, like, okay.
Yeah, here I wasn't directly drawing it because misdirecting a symbol as its nearest neighbor is the most likely, or the Q function is maximized when the error is, or the Q function is maximized when the error corresponds to the
Next element,
nearest
neighbor
neighbors.
element.
Yeah, the nearest neighbors. Yes.
So we consider the remaining as negligible and we drop it off, or we will be considering in the calculation.
No, so you have seen the union bound.
Okay, yeah, fine.
Fine. And so now, but since in case of PAM R equals, so R is a scalar 1, SM plus eta, right? All of these are real numbers.
Yes, sir.
Yes. So if SM is an interior point, there is an error. If
Yes, sir.
right, if SM equals minus M plus 1, then there is an error. If eta is greater than d min by 2, because eta is a random number, it can be positive or negative, right? If SM equals m plus 1, m minus 1, then there is an error. If eta is less than minus d min by 2, right?
Yes, sir.
Yeah, great. So now, but thankfully, probability of eta being greater than d min by 2 equals probability of eta being less than minus d min by 2 equals half the probability eta because Gaussian random variables are symmetric. Right?
Okay, sir.
So since Gaussian random variables are symmetric, we can write therefore probability of error is, so there are for MPAM there are m minus 2 interior points, 2 right? Agreed?
Yes, sir.
So the probability of error considering equal priors, that is all the signals have equal probabilities of being
So
transmitted.
shouldn't the equality interchange and half of like mod eta should be greater than d min by 2, right?
Sorry, can you say that again, Rahul?
Sir, the inequality, like the mod eta should be greater than d min by 2, right? Not
Yeah,
less than.
greater than. Yes. Fine. Thank you. So the overall probability of error can be written as m minus 2 times probability mod eta is greater than d min by 2 plus twice probability mod eta, sorry, mod eta, sorry, not mod eta, probability of error is eta is greater than d min by 2, right? Equals eta plus equals eta right?
Yes, sir.
Equals twice of and yeah, there is a 1 over m sitting over here that I had forgotten because you will be multiplying everything with the 1 over m. So this is a 1 over m sitting here, 1 over m sitting here, 2 over m, 2 q of d min by, right? This equals q of, fine. And what is the union bound in this case? Sorry, the union bound is this. So you see that the union bound is, while not accurate, so what we'll try to do is that we will try to first find the correct probability of error, but if we are unable to do so, then we will invoke the union bound, because you see that the union bound, while efficient, is not totally correct. You agree with this?
Yes, sir.
Great.
Yeah.
So this, and so now we'll talk about
Why is the union bound not correct?
so see this is the sorry, this is the exact expression. So I'll write these two expressions down. So exact is 2 into 1 minus 1 over m q of d min by n naught. Union bound is 1 q of d min by, right, and d min, if I substitute, I can get, so q of d min by equals q of 3 this beast. Fine. Basically, see, this is a measure of the SNR, the signal to noise ratio. So now you see what's the, also union bound is not exactly problematic, but you cannot, but our intention is that we cannot blindly trust the union bound.
So while deriving itself, we consider it as the maximum limit, right? So
Yes. So, so the thing is, yeah, agreed. So my point here in doing this exercise is that wherever we can find the exact probability of error, we'll find the exact probability of error. If it won't work, then we'll go to the union bound. That's what I wanted to say.
Okay, sir.
Okay, great. So,
sir, is there
yeah.
possibility to find like there are different, for example, different constellations may have different union bounds, right? Like if we, like similarly, if we start deriving a P of E for
No,
different
so
other constellations.
the union bound is unique because union bound contains this d min. The final expression of the union bound is based on the minimum distance. So the key takeaway or the key idea behind the union bound is that the performance of the error performance of a constellation depends upon the minimum distance between two symbols in it. And the distance itself, we have seen that depends on the energy that we put in that constellation.
Yes, sir. Yeah.
Right. So when you look at a constellation, the only thing that you have to see how good or how bad will it perform is what is the minimum distance between any 2 points. That is the final test for a constellation. Fine. So now I will start PSK. So yes, I will start discussing PSK and then possibly. Okay, so I believe that this is a good point to stop actually, because PSK is itself a full 1 hour discussion. So we'll stop here, and we still have that 15-minute deficit from the previous lecture that we'll cover up maybe whenever needed. Fine.
Okay, sir.
Okay, sir.
Okay. Bye. Have a nice day, all of you.
Thank you,
Bye,
sir.
sir.